Hello students, this is the second video on series LCR circuit. Part 1 of this video contains the analysis of phasor diagrams of the series LCR circuit. We find its resultant EMF, its direction with the current and all. Okay, so we find epsilon naught, I naught, the value for phi, impedance triangle. We have covered all that in the first part of this video. In this part, we are going to study about the resonance condition of a series LCR circuit. So first of all, what is the resonance condition? So a series LCR circuit is in resonance. It means that the current through it has its maximum value. Okay, so a series LCR circuit is said to be in resonance when current through it has its maximum value. So resonance condition means current through the series LCR circuit has its maximum value. Now the value for current, the maximum value for current, that is current amplitude I naught, we find a mathematical value for that in the previous part of this video, and it was I naught is equal to epsilon naught upon under root r square plus omega L minus 1 upon omega c square, if XL is greater than XC. Now if XC is greater than XL, it will be 1 upon omega C minus omega L square, but it won't affect our final answer that we are going to find. We can take any case, we'll get the same resonance condition for both. So I am here taking the case for XL greater than XC, and for such case current amplitude is epsilon naught upon under root r square plus omega L minus 1 upon omega C ka whole square. And this denominator term is actually the effective resistance, which we also known as impedance of the circuit. Now for resonance, this current should be maximum. To get maximum value of I naught, the denominator, that is Z impedance, is equal to under root r square plus omega L minus 1 upon omega C square should be minimum. And for minimum value of denominator, that is Z, the only possible way is to minimize this bracket term, because R is fixed. Okay, R is some constant, we can't reduce it without changing the resistor in the same circuit. So to reduce the value of impedance, the only thing that we can do is to minimize this bracket term, and the minimum value for this is 0. So the value of I naught is maximum when omega L minus 1 upon omega C is equal to 0, which implies omega L is equal to 1 upon omega C, or on solving it we get omega square LC is equal to 1. That means omega is equal to 1 upon under root LC. So this is the required value of omega that we have to use to get the maximum value of current. And at that instant, when we were using omega is equal to 1 upon root LC, or when this is minimum, or when the condition of resonance is there, the value of impedance is under root r square plus 0, that means R. So Z is equal to R is the condition for resonance. So when we talk about the condition of resonance, the resonance condition is omega is equal to 1 upon under root LC. The circuit at that time is purely resistive, its impedance is minimum and is equal to R. So the current and voltage are in same phase during that time, as the circuit is purely resistive. So this condition of LCR circuit is called resonance condition, the condition at which we get maximum value of current in the circuit, and the impedance is minimum, or we can say the time at which omega is equal to 1 upon root LC is called the resonance condition of the series LCR circuit. And the frequency, that frequency at which the current amplitude, means I naught, the current amplitude, that means I naught, attains its peak value or the maximum is called natural or resonant frequency of that LCR circuit. So this is called natural or resonant frequency of LCR circuit, and it is denoted by FR. So we know that omega, that is the value for omega during resonance, I am going to represent it by omega r, is equal to 1 upon root LC, and this is angular frequency. We can write it as 2 pi FR is equal to 1 upon under root LC. So the resonant or natural frequency of the series LCR circuit, that is FR, it will be 1 upon 2 pi under root LC. So this is the required natural or resonant frequency of LCR circuit. If our circuit is working on this frequency, then we are going to get resonance in that series LCR circuit. So resonance condition is when the current through the series LCR circuit has its peak value or the maximum value, means जब current का amplitude अपने peak पर होगा, then that condition is called resonance condition for that circuit, for that LCR series circuit. We know that the value for I naught is epsilon naught upon under root r square plus omega l minus 1 upon omega c ka square. And to get maximum value for current amplitude, the peak value of current amplitude we can get by reducing this value, and for that we have only one choice, putting this is equal to 0, and by putting it 0 we get the value omega is equal to 1 upon root r LC. During that time the impedance is minimum and is equal to R, which shows that the circuit is purely resistive and voltage and current are in same phase for such condition, because the circuit acts as a purely resistive circuit. So in such condition voltage and current are in same phase. The frequency at which this current amplitude attain its maximum value is called the natural frequency or resonant frequency of LCR circuit, and is denoted by FR, and we can calculate it by the help of omega r like this. So FR is equal to 1 upon 2 pi under root LC. This is the condition of resonance for a series LCR circuit. Now after this we are going to see what are the main characteristics of a series resonant circuit. If a circuit is showing resonance, then what are its characteristics, that we are going to sum up now. So if we have an LCR series circuit in resonance, then what characteristics it show, that we are going to discuss now. So the very first thing is, in such circuit the resonance occurs only when omega L is equal to 1 upon omega C. That means XL is equal to XC. This is the first characteristics of such circuit. So for a resonant series circuit, series LCR circuit, XL must be equal to XC. This is the first characteristic. Second is, the resonant frequency for such circuit is 1 upon 2 pi under root LC. This we have calculated just now. The resonant frequency is 1 upon 2 pi root LC. Third thing is, the impedance is minimum and purely resistive. Z is minimum and Z is equal to R. That means purely resistive. No reactance will participate in impedance in such situation. So the circuit has minimum impedance and it is purely resistive. Since it is purely resistive and minimum, so the current has its maximum value. I naught is equal to epsilon naught upon R, has its maximum possible value. This is the fourth characteristic. If I naught is equal to epsilon naught upon R has its maximum value, then the power dissipated in the circuit is also maximum. Power dissipated is maximum and is equal to, and this power is equal to epsilon RMS square upon R. This is the fifth characteristic of such circuit. Next thing, if we see the power factor. Now what is power factor? We haven't discussed it yet. So power factor is actually the term called cos phi. Cos phi को ही हम power factor भी बोलते हैं. And if we see the impedance triangle, it is like this. This is phi, hypotenuse is Z, base is R, and this is XL minus XC का XL minus XC or XC minus XL depending upon which is greater than the other. If XL is greater, then XL minus XC. If XC is more, then XC minus XL. So cos phi according to this is equal to R upon Z. According to the impedance triangle, cos phi is equal to R upon Z. That is base upon hypotenuse. So for a series resonant circuit, the value of cos phi is equal to 1. Why it is 1? Because Z is equal to R in case of resonance. Z is equal to R, and then cos phi is equal to 1, which implies phi is equal to 0. So we get the condition of resonance when phi is equal to 0 or the current and the EMF are in same phase. The angle phi is 0. Next characteristic of such circuit is that series resonance can occur at all values of resistance, because the condition omega is equal to 1 upon under root LC doesn't depends on resistance. So it is independent of the value of resistance. That means series resonance can occur at all values of resistance capital R, and the voltage across R is equal to the applied EMF. Okay, the another thing is the voltage across R is equal to applied EMF. So in such circuit, the voltage across R is equal to the applied EMF. The next characteristic is that the voltage across L and C, that means VL and VC, are equal and have a phase difference of 180 degree. So their resultant is 0. That's why the whole EMF appears across R. So the next characteristic for such circuit is that VL and VC, voltage across inductor and capacitor, are equal and have a phase difference of 180 degree. That means they will cancel out each other and their resultant is equal to 0. This is the another characteristic. Another thing is that the voltage across L and C are very high as compared to the applied voltage. So next thing that we have to note is that values for VL and VC are very high as compared to the applied voltage. This shows that a series LCR circuit can be used to obtain a large magnification. Means जो value हम लगा रहे हैं उससे ज़्यादा हमें मिल रहा है, that means it is used for large magnification of AC. And the last point is that this series resonant circuit is also called an acceptor circuit. It is also known as an acceptor circuit. Now the reason is that whenever we apply a number of frequencies to this circuit, it accepts only one frequency, that is its natural or resonant frequency FR, and reject all other frequency. So the current is maximum for this frequency and it accepts only the frequency equal to FR. So acceptor circuit बोलने का meaning इसका ये है that it accepts only one frequency, that is FR, and give maximum current for this. So these are all the characteristics of such series resonant LCR circuit. Now after these characteristics, we are moving to the another new factor, that is called sharpness of resonance. So we have a resonant circuit and now we are going to define its sharpness. To understand the sharpness of resonance, we plot this curve between the angular frequency omega and current amplitude, that is I naught. And what we observe is that current amplitude has a peak value at resonant frequency omega r. Okay, so omega r, that is the resonant frequency, it has value 1 upon under root LC and is fixed, and at this value the current amplitude has its peak all the time. But this frequency is independent of the resistance in that circuit, but the sharpness of the peak depends on R. So the thing that we have to understand is the angular frequency is independent of resistance present in the circuit. It doesn't depend on the value R, but current amplitude shows peak that depends on the value of R. How it varies is the peak is higher for smaller values of R and is sharp for the smaller values. That means jitna resistance की value low होगी, we will get that much sharper peak in the graph. So this is the low value of R, okay, and this is the high value of R, while this one shows the medium range or the moderate value of R. So jitna resistance low hoga in that series LCR circuit, the current amplitude will show a sharper peak. Although the peak will remain at the same point, that is the omega R, this angular frequency won't change, it will remain same for all the values of R. We will get the resonance at the same point, that maximum value at the same point, but the sharpness of the curve will vary according to the value of R. If the circuit has low value of resistance, the peak is higher and vice versa. So the sharpness denotes the relationship between resonance and the resistance, and it shows that the resonance is sharp for small values of R and flat for larger value of capital R. So we can conclude all this as the current amplitude, that means I naught, the current amplitude has its peak always at omega r, which is equal to 1 upon root LC, and falls to 0, that means it reduces in both directions, falls to 0 in either directions. This resonant frequency omega r is independent of R, but the sharpness of the curve that we get, sharpness of peak, depends on the value of resistance, that is capital R. Now how it depends is the peak is higher for smaller values of R and flat for higher values of R. That means if peak is higher, that means the sharpness of resonance, the resonance is sharp for small r. This implies that जो हमारा resonance होगा, that will be more sharp in case of smaller values of R. So we can write it as the resonance is sharp for smaller values of R and flat for larger values of capital R. Now this sharpness of resonance, this we understand that itna jab small r hoga then resonance is sharp, and jab large r hoga then it will be flat. But this sharpness of resonance is measured by a coefficient called the Q factor or the quality factor of the circuit. So the coefficient by which we can measure the sharpness of resonance is called Q factor or quality factor of the circuit. So quality factor or Q factor is the coefficient by which we can measure the sharpness of resonance in that circuit, and that Q factor belongs to a particular circuit. So till now we have studied that sharpness gives us the idea that how sharp the peak is. If we plot a curve between the current amplitude and frequency, then sharpness of peak depends on R, and it gives us the idea that how much large the value of I naught is for that particular circuit. And resonance is sharp for smaller values of R and flat for larger values of R, and the coefficient that by which we can mathematically measure the sharpness of resonance is called Q factor or quality factor, and it is defined as, this Q factor is defined as the ratio of resonant frequency to the difference in two frequencies taken on both sides, two frequencies taken on both sides of resonant frequency such that each frequency has current corresponding to it that is 1 upon under root 2 times of current amplitude, means of I naught. So these are those two frequencies corresponding to which the current is 1 upon root 2 times of I naught, and Q factor is defined as the ratio of resonant frequency to the difference of these two frequencies. So suppose if these two frequencies are omega 1 and omega 2 and resonant frequency is omega r, then Q is omega r upon omega 2 minus omega 1. Okay, so this will be more clear by the diagram that we are plotting next. So here, as we can see in the diagram, this is the curve for a particular value of r. At omega r we are getting the peak which corresponds to the current I naught, equals to epsilon naught upon r. Then we mark those frequencies which corresponds the current. I is equal to 1 upon root 2 times of I naught, and these frequencies are omega 1 and omega 2. The difference between omega 1 and omega r is delta omega. Again omega r and omega 2 is delta omega, and this whole difference is 2 delta omega, which is called bandwidth. So Q is the ratio of omega r to the difference between these two frequencies, and these two frequencies are those frequencies which corresponds the value of current equals to 1 upon root 2 times of I naught, and this difference we call at bandwidth. So we can give the formula of Q is equal to omega r upon omega 2 minus omega 1, and this omega 2 minus omega 1 is actually equal to 2 delta omega. So we can write it as Q is equal to resonant frequency upon bandwidth. Bandwidth is equal to 2 delta omega. This is the value for Q factor. Here omega 1 is omega r minus delta omega, and omega 2 is omega r plus delta omega. So when we find omega 2 minus omega 1, it is 2 delta omega. Now we can also find expression for Q factor in terms of L, C and R. So we are going to find the expression for Q factor. So for Q factor, we have three frequencies with us, that is omega r, omega 1 and omega 2. Now at omega r, it is the resonant frequency. We know that the impedance is equal to r, and at omega 1 and omega 2, the value for Z is under root 2r. Okay, at omega 1 and omega 2, the value for impedance is under root 2r. So Z is equal to root 2r means we have under root r square plus omega L minus 1 upon omega c ka whole square is equal to root 2r. On squaring both sides, we get r square plus omega L minus 1 upon omega c ka whole square is equal to 2r square, and on solving this we get omega L minus 1 upon omega c is equal to plus minus r. We take it here, it becomes r square, and taking root again we get omega L minus 1 upon omega c is equal to plus minus r. So one is for frequency omega 1 and the other one is for frequency omega 2. Omega 1 is on the left side, so it is minus r. Omega 2 is on the right side, so it is plus r. This implies that omega 1 L minus 1 upon omega 1 c is equal to minus r, and omega 2 L minus 1 upon omega 2 c is equal to plus r. Let it be equation 1, and this one is equation number 2. Now on adding these two equations, we get, on adding equation number 1 and 2, we get this equation, and on solving this we get that omega 1 into omega 2 is equal to 1 upon LC. Now this is the result that we get by adding 1 and 2. Now next we are subtracting 1 from 2. This is adding 1 and 2. This is subtracting 1 from 2. While subtracting 1 from 2, we get that omega 2 minus omega 1 into L plus 1 upon C, omega 2 minus omega 1, omega 2 is equal to 2r, and on solving this we get omega 2 minus omega 1, that is common, and in the bracket we get L plus 1 upon C omega 1 omega 2 is equal to 2r. On solving this and substituting the value of omega 1 omega 2, that is 1 upon LC, C and C will cancel out, and on solving this we get omega 2 minus omega 1 L plus 1 upon C into 1 upon LC is equal to 2r. That means it will be omega 2 minus omega 1, and the C and C will cancel out and L will go on the numerator side, 2L. We get 2L here is equal to 2r, which implies omega 2 minus omega 1 is equal to r upon L. Okay, so we have omega 2 minus omega 1 is equal to R upon L, which is our bandwidth. This is 2 delta omega. Hence, the Q factor Q is equal to omega R upon 2 delta omega is equal to omega R upon omega 2 minus omega 1 is equal to omega R upon L. It implies the Q factor is equal to omega R L upon R. This is the expression of Q in terms of L and R. And we also know that omega R is 1 upon root LC. We know that the resonant conditions say that omega R is equal to 1 upon root LC. So Q is equal to 1 upon under root LC into L upon R. On solving this, we get 1 upon R under root L upon C. So this is the required value of Q factor in terms of L, C and R. Means if we know the values of resistance, inductance and capacitance present in that particular series LCR circuit, we can find its Q factor. If Q factor is large, that means if R is low or L is large, the bandwidth 2 delta omega is small. This means that resonance is sharp or the series resonance circuit is more selective. So this implies that Q factor, agar Q factor is large, that implies R is small, right? R chota hai, R is low, or we can also say that L is large, or in this case 2 delta omega, the value for 2 delta omega, that is R upon L, is low. This is also small, and if this value is small, the value of Q is large, and this implies that the resonance is sharp. Q factor is large implies that resonance is sharp, and resonance sharp actually means the circuit that we are using is more selective. This is the meaning of sharp resonance. If a circuit has resonance that is sharp, then it means that that series circuit is more selective. It pick its natural frequency in a more selective manner. Okay, so this is the Q factor, and Q factor tells us that whether the resonance of the circuit is sharp or not, or how sharp it is. This value is given by the Q factor. So this is about the resonance in series LCR circuit. For further videos, stay tuned and keep studying. Thank you.